to give the example of a call option. Okay? So we're going to consider a call option with strike price P. Okay? And just to remind you what that is, here you can buy a share at a price P. Okay? And you can make a profit X of T, and that should be a capital X. Apologies for my typos. Hi everyone. And thus making a profit X of T of P, where X of T is the price of the stock at time T. Okay? Here, the share, or when I say share, I should actually say option, so another typo. Here the option must be exercised by time T. Okay? And we're going to assume that the stock price, X of T, satisfies the equation that at each time, the new value of the stock price is the old stock price plus some IID random variable with finite expectation. Okay? So basically, the stock price is a random walk. Okay? Really, it should be a geometric random walk, but we're just doing random walk. Okay? And at any point in time, you can decide to exercise the share. Okay? So this isn't a call option where you, at the end of time T, you can exercise the share, which I think is, I forget which one's American option and which one's European option. I think this is a European option. Does everyone agree with that? So American option is where I think at time T, you basically you have to exercise the option, otherwise it expires. And European option is one where at any point in time you can exercise the option. Is it the other way around? Oh, okay. European option is the one we exercise at time T. Yeah. Okay. Yeah. Fine. Okay. Time T, you can exercise the share, the option, whereas American option, at any point in time you can exercise the option. Okay. Sorry. Good. Okay. Thanks. Good. You can see my day job isn't necessarily doing financial control problems, but well, doing control problems is my day job, and doing financial examples is just good fun. Okay. Good. Right, so the question asks to find some kind of qualitative properties of the share price to show that it's decreasing. So we're going to show that there's a decreasing sequence of prices, A of T, such as optimal to exercise whenever X of S is bigger than A of S. Okay? So it's a little bit like the stock price, a little bit like the car situation, where maybe we don't want to exercise too early if the price is really high, but if it is sufficiently high, then we might decide, all right, that's the time to exercise the stock option, okay? And then as time gets closer and closer to the deadline, maybe we want to kind of depreciate our price, okay? Does that make sense? So it's the same sort of rationale as the revenue management problem, okay? Except for probably the main difference is in the revenue management problem, the way that it was decided to purchase the car was according to this probability, which was sort of independent but dependent on the price. And every time, now the price isn't necessarily a figure, doesn't matter anymore, but now the state of the system is evolving according to some Plant equation in a much more meaningful way. Okay, so it's a slightly more sophisticated version of the previous problem. Okay. So let's go through the solution of this. Okay. Okay. So we're going to show that the value function W of t minus s, okay, oh sorry, W of t, I'll just do W of t, sorry, little t, let me get it right, okay, of x, okay. So that means we're at time t, the value of the stock is x, and w is the most amount of money I can expect to make by making a decision when to stop and exercise the share option, okay? I'm going to show that this is such at 1, Wt of x is decreasing in t. Then we're going to show that Wt of x minus x is decreasing in x, and 3, Wt of x is continuous in x. Okay? Okay, I'll just zoom this in a little bit. Okay. So, I wouldn't ask you to solve the problem in this way in an exam. I wouldn't just state exercise 6 and expect you to solve it. I'd probably say it to you in a number of stages. So say, show 1 that x of t is decreasing, show 2 that x of t minus x is decreasing, show 3. So don't think I'm just going to give you an exam question that says this, if you see what I mean. But I want to see how this breaks down into different parts. Okay? So, what is kind of the one thing that I've been telling you to do whenever I tell you a dynamic programming problem or a markov decision process problem? So this is the one thing I kind of one of the take-home messages from the tutorial yesterday. Yeah, great. Bellman's equation. Yeah, so you should always just have it in your mind. Neil's going to ask me something about Bellman's equation probably somewhere. Okay, so we're going to write down Bellman's equation for this problem. Okay. And it's one of the things I really want you to get used to kind of doing. So let's look at the Bellman equation for this guy. Well, let's first think about the termination condition. So at the final time, capital T, you don't even need to give the solution here necessarily, but I've basically got two choices at time t, okay? Either I can exercise the option, or I cannot exercise the option. I can't wait further to the next round, because it's the end of time, it's going to expire at time t, okay? So, let's think about the two things that can happen. So, if I decide to exercise the option, what is my profit? Yeah. So it's, x capital T, or in this case I've told you the state is little x, minus p. So perfect. Okay? And if I decide not to exercise the option, it's 0. Okay? And so, if I've got a decision to make, which should I choose? This one or this one? Well, I mean, it depends, but you're basically going to choose the bigger of the two, aren't you? You can say, well, if this is positive, I'm going to exercise the option and make some money, and if this is negative, then it's better not to exercise the option and I don't make any money, but I don't lose any money either. Okay, so it's the maximum between these two. Okay? Now, what Bellman's equation does for us is it gives us a way of linking the properties of the function at time capital T minus 1 to capital T minus 2 and so forth backwards. Okay? So you can quickly notice that this function is decreasing in t. Well, it's nothing to do with t. Well, you can check it's decreased. Wt of x minus x is decreasing in x, and you can also check that it's continuous in x. Okay, so sort of hoping that that property is preserved as we kind of use Bellman's equation to relate the problem at time capital T to the problem at capital T minus 1. Okay, and so forth. All right. So again, the principle's the same. I want to relate the decision that I want to relate the optimal reward at time t to what will happen if I make the decision to exercise the option or not exercise the option through to the next round. Okay? So, I'm sitting at time t, the stock price is x, and I've got two decisions I can make. I can either exercise the option or not exercise the option. So if I exercise the option, okay, my action is exercise the option, how much money do I make? What's the profit? So remember that once I've exercised the option, that's the end of the game. Everything's finished. There's no future rewards to make in the future. And I can tell you that you've already told me the answer up here. Yeah, x minus p again, yeah? Because if I exercise the option at time t, then I've got x from the stock, but I was able to buy it at price p, and that's my profit. Okay? So it's exactly the same. And then do I make any money in the future? No, nothing. Okay, because that's all the profit I'm going to make. The option is expired, and that's the end of the time. Okay? So if I just relate that back to here, what that's saying is my instantaneous reward here is x minus p, and once I've exercised the option, the future optimal reward is 0, because there's no more money to be made. Okay? All right. So that takes care of one of the actions in this Markov decision process, and the other action is that I don't exercise the option. Okay? So how much money do I make at time t if I don't exercise the option? At that moment in time, does anyone give me any money? 0. I don't get anything. Yeah? So at this point, the reward, if I don't exercise the option, the reward is 0 for the time instant, and I just go on to the next round with the stock option where I haven't exercised it, and it moves to its next state. Okay? So we'll cover these in a bit more detail, but this is just a kind of typical of a kind of stopping problem. So at the next round, if I don't decide to exercise the stop option, I move to the state x plus, well, epsilon, where the epsilon of t, yeah? And then I have to make the optimal decision from there on out. Okay? So that is the money that I make if I exercise the option, and that is the money that I expect to make if I don't exercise the option at time t, but I make optimal decisions from there on out. Okay? And again, the principle's the same. I look at which is bigger. Do I make more money from exercising the option now, or do I get more money from waiting? Okay? And so I choose the biggest between those two. So it's going to be the maximum between these two. Okay? So that's the Bellman's equation for this, okay? Okay. All right. Now let's think about these different properties. Okay. So first one, I don't really actually need Bellman's equation for this one. So let's think about Wt and Wt plus 1. Okay, so we're going to ask the question, is Wt decreasing in t? So we've got Wt of x optimizes over t rounds. Sorry, t minus t rounds. Okay? And think of this. So what are the actions that I can choose from here? Okay. If I start at x, and I'm at time t, then I've got this many rounds to make a decision as to when to stop. Okay? Whereas if I look at this guy, it's the same problem. Okay? So it's the same problem, but over one less round. So what do I mean here? I mean, the sets of actions I can make are stop at time t, stop at, well, let's think of this, I can stop at the first round from here, so I can stop now, or I can stop at the next round, or I can stop at the next round, or I can stop all the way up to the t minus little tth round, okay? I've got that many opportunities to stop, okay? So any policy I can do, well, okay, here I can stop at the first round at this time, or at the second round, all the way up to the capital T minus T minus 1th round, okay? So any policy that I can implement here, I can also implement here, okay? In other words, the sets of policies that I'm allowed to do have one extra time round here compared to this one, okay? So in other words, what I'm saying is, the sets of things that I'm optimizing over here, the sets of actions or the sets of things that I can optimize over is a larger set than the set of things that I can optimize over here. Does that make sense to everyone? Yeah? So if I'm optimizing over a bigger set, okay, in this one compared to this one, it must be that this is bigger. Yeah? It's like saying I'm maximizing over 3 variables compared to when I'm maximizing over the same problem but with 2 variables. Okay? Okay. So concretely, we can think of the sets of policies that are available to me from time t plus 1 onwards are a subset of the sets of policies from time t. Okay? So Wt of x, which is equal to the max over the sets of policies from time t, where I maximize my reward function x of pi, is always going to have to be less than when I maximize the same reward function, okay, but over a smaller set. Okay? Okay, so that means we've done this first part. Tick. Okay? Now, the second and third part we're essentially going to prove by induction, going backwards. So we can see that the properties are preserved here, that if I minus off x from here, I'm going to get minus p max minus x, okay, which is a decreasing function. It's also a continuous function. Okay? Okay, so let's write that down. Oop. So 2 and 3 hold since the max and the mean of a continuous decreasing function is continuous and decreasing. In particular, i.e., if I look at this function, the value function minus x, it's the max minus p of e of wt plus 1 x plus epsilon of t minus x. Okay? So that's just my Bellman's equation, but I've minused x off both sides. Okay? So notice, provided what's inside here is a continuous function in x, then the expectation is going to be a continuous function in x. And the maximum here, when applied, is also a continuous function as well. So it just preserves the continuity property over here. Okay? Further, if this is a decreasing function in x, then the expectation is going to be a decreasing function in x. And further, if I take the max between a constant and a decreasing function, it remains decreasing. Okay? So then it remains decreasing over here. So provided this has the properties of being continuous and decreasing, then so does this preserves that property over to this expression here. Okay? We'll just go back. Okay? So notice that this is a continuous and decreasing function, so it just has to preserve itself. Since at time capital T we start with a continuous decreasing function, at time capital T minus 1, it must be a continuous and decreasing function because it satisfies Bellman's equation. Okay? And that preserves the properties, and so forth and so forth. Okay? So that's why, so i.e. this is continuous and decreasing provided wt plus 1 is, or, well, let me be a bit more precise there, wt of x plus epsilon of t minus x is. Okay? Right. So now for the final part. So we've kind of answered what these properties have asked of us. So we've kind of said this and this. Okay? But the question was really to say that show that there exists a decreasing set of prices such it's optimal to exercise the option whenever the stock price goes above that price. Okay? So you're kind of constructing a boundary. Okay? And whenever the stock price goes over that boundary, then it's optimal to exercise the option. Okay? So why is that? And we can really just do it by drawing a picture now. So let's look. So let's look at when we make the decision. So if this is the maximum, then we know that it's optimal to exercise the option. Okay? And if this is the maximum in this expression, we know it's optimal to carry on till the next round. Okay? So let's have a look at that. So we can imagine a kind of typical picture of what's going on is that we could have we can plot over here the line minus p, okay, and then as a function of x, we can plot the expected value of wt plus 1, x plus epsilon minus x, okay? And we know that it's a decreasing continuous function, yeah? Okay, this is a decreasing continuous function, so it's going to look something like this. It's going to start somewhere up here, and it's going to decrease. Okay, that is what E of wt plus 1 x plus epsilon t minus x is going to look like. Okay. So there's going to be some point here, which I'm going to call A of t, okay, where whenever x, the stock price, is in this area, okay, then the maximization is given by this term. Okay, so you don't want to exercise the option. Okay, and then whenever we're on this side of the line and minus p is the bigger of the two lines, then we want to exercise the option. Okay, and then we said that the function is also, let me just recall, the function is decreasing in t, okay? So the function at time t is going to be a bit bigger, okay? So if I drew the line for time t here, it's going to be a bit above that line, okay? And here, that would give me the decision that I should be making at the previous time. Okay? So as time progresses, what's going to happen is these curves are going to kind of go down until eventually they reach a kind of straight line, okay, where at the final time it looks like the curve x minus p max 0, okay? So these curves are eventually going to come down, and then we're going to end up with the line, well, actually it'll be minus p max minus x, okay? So it'll end up being that line, and that'll be the final strike price, yeah? It'll be, but we'll start with saying, like, at the beginning, we're going to have quite a high threshold. We're going to say that only if the stock price gets really, really big is it going to be worth my while to try and exercise this stock option, okay? But as time gets bigger and bigger and we get closer to the expiry date, it converges to this line, okay? A straight line at strike price P, okay? Where it's only worth exercising the option if the value of the stock is above X, okay? So those are kind of the basic properties of what the optimal policy would be for exercising a American option, yeah? Now, if we wanted to do numerics on this, if we knew what the fluctuations were of the stock option, this epsilon, we could then go back also numerically solving by recursively these equations for these fixed points, where this is equal to P. Okay? All right, so we'd kind of numerically solve for this equal to P, and then iterate back, so I'll solve for that. Okay? And each of those will give me the optimal decision kind of boundary. Okay? But that's sort of the qualitative properties of how you should go about solving a so optimally exercising an option. Okay, so so this is kind of the difference. This is stepping back a bit. This is a little bit the difference between what you've been doing in, say, your stochastic integration course, where you've been taught how to price an option. So you're like Goldman Sachs, and someone comes to you as a company, and they say, "I want to buy this stock option from you. How much is it going to cost?" Okay, and that's where Black-Scholes comes in, and where the kind of theories used there and quants and investment banks work with, okay? But there's this other side to it, where someone actually buys a stock option, and then you've got to decide how am I going to use it? What's the best way for me as a company, say, to exercise that stock option? That's the other side of the kind of financial problem, which we're a bit more focused on in this course, okay? So that's about pricing, more about like, well, I've got some financial products, or I've got to do some wealth management for a number of people who've got money and they want to give it to me, and I want to try to invest it in a good way, okay? All right. Okay. So I'm going to do another example, which is a bit more of a silly example, but this is like, people also want to know how the exam's going to look. And this is kind of more like an exam type of question, yeah? Okay. I thought of this question last year because I bought a goldfish. It was still alive. So it wasn't very expensive. It's £2.50, but anyway. So you own an expensive fish, okay? So you own expensive fish, okay? Each day you're offered the price for the fish, okay? And it's according to some distribution, f of x, okay? You can either accept or reject this offer. With probability 1 minus p, the fish dies that day, okay? All right, my fish is still alive, so it's good. We bought 2 fish, 1 died actually, so I'm kind of, okay. We could ask the generalization of this question with 2 fish, I think, as well. So that's an interesting question, actually, yeah. It's not on your exam, but it's an interesting question. Okay. Find the policy that maximizes the profit from selling the fish, okay? So you've got a good, it's going to expire at some point in time, at some random point in time, okay? How are we going to go about solving this? Okay, fine. Okay. So let's do the answer for that. Okay. So one of the reasons that I sort of asked this question a little bit is because, well, actually, there's a question at the end of the tutorial yesterday about this, so it kind of covers that a little bit. So I'm going to let D be the day that the fish dies. Okay. I'm going to let X of t be the price offered on day t. Okay. I'm going to let R be the optimal reward. And I'm going to let A of t be the action that you decide. 1 if you decide to sell the fish, and 0 if you decide not to sell the fish. Okay, now, so the reason I've asked this question is you can notice there's something different about this question to the previous ones. So, kind of the issue here is that previously all the questions we've done so far have said, okay, we've got t units of time at which to exercise an option, or we've got t units of time to sell a car, okay? In this question, there's no final time, okay? The game doesn't stop until the fish dies, and the fish dies just when it dies, you know? Yeah? Who knows when that is? Hopefully has a long, fruitful life, you know? And so this is kind of what this example is leading on to, is what we're going to do in the next section, which is where there isn't a definite end time, okay? And notice that what we were doing previously was starting at the end time and then inductively working backwards to time 0, okay? And this is a problem where we can't do that, okay? So one of the things I'm trying to convince you with this question is that you can still use Bellman's equation, and that still there's a way of solving this question. So although we can't rely on this induction type of argument starting from time capital T and working our way back to time 0, actually some of the devices that we used, in particular Bellman's equation, still hold. Okay? And so we can still work with Bellman's equation even if we don't have this kind of induction tree type argument anymore. Okay? All right. So let's look at what the optimal reward looks like. So I'm just going to write a few things out, which we'll do in a little bit more abstract form in the next class. Okay, so the optimal reward R, I can write down as now a sum over time of x of t times a of t. So if at time t this is a 1, then I'm going to get x of t, which is the price offered. Okay? But then we've got the issue that you can only sell the item if the fish hasn't died yet. Okay? So I need the time that the fish dies to be bigger than t as well. Okay? And then the thing to note is this sum isn't from time t equals 0 up to time capital T, but it's a sum from time equals 0 to infinity. Okay? Next thing I can note is that the time that the fish dies is actually independent of x of t and a of t. Okay? Notice that this is a geometric random variable. If I know that I've got up to time t, the sets of decisions that I've made about selling the fish or not, and the prices that are offered so far don't do anything to determine when the fish dies. Okay? So that's independent of that. Okay? So I can notice that this is really p to the power of t. Okay? X of t, a of t by independence. Okay? So I think that's sometimes called like the role of independence or something like this in kind of measure theory books and things like this. Yeah? Okay? Next thing I'm going to do is I'm going to condition on the price, okay, and then look at what happens. Okay? So I can condition on x of 1. Okay, so I've now sort of, I started from time 0, so I should probably have a 0 on that. Apologies. Okay. Okay. So now I've got a choice. I've been given an offer, x0, and I've got to decide if I'm going to accept it or not. Okay? So then we can look at what this function inside here looks like. Okay? So So now notice okay, so I've got two choices here. Either I accept the offer, or I don't accept the offer. So if I don't accept the offer, or I accept the offer. Okay? And depending on my decision, that affects what this term is going to be. All right? So, first of all, the easy case, let's suppose I accept the offer. I've been given an offer of x of 0, and my action is whether I accept it or not. So if I accept the offer, how much money do I make? Yeah, exactly, x0. Yeah. Because once this fish is sold, I don't have the fish anymore. It's sort of the end of the actions, okay? Now, what happens if I decide not to sell the fish? Then I'm going to essentially go to the next time, okay? And I've basically skipped the first term in this sum. Okay, that's set equal to 0, but I'm still left with the same problem. Okay, so we're going to end up with E with the sum t equals 1 to infinity p of x of t of a of t. Okay. And then I could put this with the power t, but I'm going to put a power t minus 1 on here, and put a p of t here. Put a p here, sorry, just a p. Okay? Oh, I'm just realizing I forgot the 0 there as well, apologies. Okay. So here I've gone from something which was a sum from t equals 0 to infinity of p to the t. So I've got p to the 0, p to the 1, and then the states and actions. Here I've got something that's p to the 0, p to the 1, and then the states and actions again. Okay? So assuming I make the optimal action choice from here on out, what is that equal to? So what's the difference between, say, that and that? Well, essentially nothing. It's exactly the same problem. I'm faced with, at time 0, I get p to the t, and then I've got independent prices coming in and actions, okay, that I can make. Here it's the same. I start with p to the 0, and then I've got independent prices coming in, and I've got actions whether to accept them or not. So it's exactly the same problem again. Okay, so the problem's just iterated itself, okay? So in other words, what I'm saying is that is just equal to R again, okay? So then the question comes, which should I choose? Should I choose to accept the offer x0 and get x0, or not accept the offer and then get p times R? Okay, so what would you do under the optimal policy? You're trying to maximize rewards, so you choose probably the bigger of the two. Okay, so you just go like, I'm going to choose whichever's bigger. That's going to be the best decision. Okay. So the optimal policy choice to choose the biggest of p times r and x0. Okay? So putting this all together, if this is going to be my optimal reward, and if here, for this expression, I'm going to make the optimal action choice, okay, I'm going to end up with the following expression. So the R is equal to the expected value of the best of these two. Okay? So it's going to mean the maximum of PR or x0. Okay? Okay? So what we're going to end up with here is basically exactly the kind of Bellman's equation for this type of problem. Okay? So this is, again, okay? So one of the things to notice about this Bellman equation, which is a little bit different, is that previously, so just going back to the Bellman equation here, where it went from time 0 to capital T, okay, here I related the optimal value function at time t to the optimal value function at time t plus 1, okay? So there's a subscript here in t, and there's a subscript here of t plus 1. Okay. Here, we're relating the optimal value function at time 0 to the optimal value function at time 0 again. Okay? So we're actually kind of looking for a fixed point rather than an iteration, looking for a fixed point. Okay? Of course, you can solve fixed points by iterating, but okay. Another thing you can notice, this is just more of an aside, it's not critical to the solution here, is that notice that if I minus RP off both sides, notice RP is essentially fixed here, okay, then I'm going to get E of max, it's a little bit like before, 0 x0 minus PR, okay. So given that this is P is a probability, this is an increasing function in R, and this is a decreasing function in R. Okay? So we've got a line going up like this, we've got a decreasing function going down, and where those two functions meet each other is going to be the fixed point solution. Okay? So this is strictly increasing, and this is decreasing, at least decreasing, in R. And so if I was to plot both of these functions in terms of R, then I'd have a line that goes up with, and I'd have a line that goes down, something like this. Okay? And the point in the middle where the two lines meet this point here is the optimal price to take. So anything above this price, above this offer, you want to accept. Anything below this offer, you say, I'm not going to sell the fish. Okay? I mean, the answer to the problem is not so important, but the formulation of it is more important here. Okay? So I just add the note that, so there exists a unique optimal price above which you sell the fish. Okay. Okay, right, well, we probably have like a good 10-minute break now, and then I'll start to kind of develop a bit more theory of these kind of infinite time problems.